logarithms.
Yes, what's it? What is it?
What happens to a square root within a logarithm? I'm not too sure if I remember the rules on that.
Okay, let me see if I can go to the white screen and show you. Well, if let's say it was a logarithm of the square root of x plus y, right? So the square root is inside the logarithm. Then you would realize that a square root is considered a half power, and so what you would get would be that. Ah, here's a bunch of people now coming.
Okay.
If the square root was, like that, there's really nothing you can do to it. I mean, that's as good as it's going to get.
Okay, so if something's within the boundaries of a natural log and it's square rooted, it just brings it out.
As a half power.
Yeah, okay.
Cube roots are 1/3 power, and so on.
So on and so forth.
Yeah. Oh, good. We're getting more people.
Happy Friday, Mr. Robertson.
Happy Friday to you. How is things, Reese?
Pretty good.
Living the dream?
Mm-hmm.
Good. And I think it's time for us to get started. Oh, got a couple of stragglers coming in. There we go. Well, good morning, everyone. First thing is those questions involving partial derivatives and obtaining the values from tables, the chain rule section. I put a solution to one of them online, as I promised. So if you go hunting for it, I think I put it inside PDF help. So if you go into the main menu, you look for the one where all the lectures of other people are, and at the bottom you'll find two different sections. One has got all the PowerPoints and the other has PDFs. So I believe that's where I put it. So you'll be able to get it there. Last time we kind of just superficially started looking at directional derivatives. So let's look at them in a little bit more organized fashion. A directional derivative is basically a normal derivative in the Calc 1 sense, which means a directional derivative will be a number, and that number will be an indication of how steep the surface of a function would be at any given point if you try to walk in whatever the direction of the vector u is. So that's kind of what it is if you're trying to figure out what you're calculating. And before we do the whole directional derivative thing, let's focus on a subproblem. There's a guy called the gradient vector. We use this upside down triangle and we pronounce this as delta. So we say the gradient vector delta f, or sometimes we just see this and we say the gradient vector. And the gradient vector of any given function, say z equals f of xy, is simply just a vector formed by differentiating the function with respect to x, and that goes in the first component, and then differentiating the same function with y. And over here I've got the same basic formula, but in a little bit more concise version. So let's show you how that would work. Now, suppose that we had that function. If you wanted to get its gradient, Sometimes they don't put the x, y, sometimes they do. It's the same thing. Then you differentiate with respect to x, and you differentiate partial derivative with respect to y. So the x component of the gradient vector is what you get when you differentiate this with respect to x. So there's 3x squared e to the y. That gets you nothing, and that gets you y. And then to get the second component of the vector, you differentiate partial derivative of this fella with respect to y, in which case you'll get an x cubed e to the y. You've got a plus 2y and an x. And that is the gradient vector. Now, sometimes you're being asked to get the gradient vector at a given point, for instance, at the point 1, 0. When you see that, you have to recognize that the x is 1 and the y is 0. So you get your general version, and then you just plug in every time you see an x is 1, every time you see a y, you get 0. So let's see what that looks like. 3 times 1 squared e to the 0 plus a 0. 1 cubed e to the 0 plus 2 lots of 0 plus an x. In this case, 3 times 1 is 3. 3 plus nothing, still 3. And this is 1, this is nothing, this is 1 is 2. So the gradient vector at this particular point is 3, 2. Now, you remember from on Calc 3 vectors, this is quite a common notation. It is acceptable, but I prefer not to do it. Isn't it also acceptable to use the IGI notation when you describe vectors? It isn't any different, it's the same guy. I prefer this, it's just more concise. So what you're going to do with this vector, what does this gradient vector at this point does? It actually tells you something quite interesting. If you have a surface and you choose, say, this point, which is 1, 0, can we pretend that this point here is 1, 0? So imagine you're on a hill at that particular point, right? So 1, 0, whatever the z coordinate. At that particular point, this direction, right, in terms of the horizontal ground, going 3 in the x and 2 in the y, kind of thing, like going in this direction, or if we can pretend that's what it was. This is the direction of steepest descent. It means at that point on the hill, if you walk that way, it's going to be the steepest, the biggest positive number or the biggest numerical value. So that's kind of interesting that it does that. Let's do a couple more examples of just calculating gradients, and then we'll see what that looks like. So suppose I have a function and it's x squared plus y squared, and it's inside the big square root. Then it's gradient vector. Well, if you're going to do this question, you probably should write it like that. So partial derivative is 1/2 x squared plus y squared to the -1/2 times the derivative of x squared plus y squared with respect to x, which gets you another 2x. And if you do the y guy, you get a very similar looking answer, but you finish with the times 2y. If you tidy this up and make it look pretty, so you take this surface, and this is what its gradient vector would look like. Suppose that was your surface. Then your gradient vector would look like this. If you differentiate this, it's a chain rule. You get 1 over x squared plus 2xy times the derivative of this with respect to x, which gives you this guy. If you do it with this guy with respect to y, you get 1 over x squared plus 2y. If you differentiate this with respect to y, you get 2x. So this process that we're looking at allows us to find a very special vector called the gradient vector. And this gradient vector is related to the steepness of the hill at any given point. So if you plug in any given x and y, the gradient vector will tell you the direction of that you should travel if you want to go up the steepest. If the function was representing temperatures at various points, then the gradient vector might be the temperature gradient. So I don't know if you've ever heard of a term like the temperature gradient and you're thinking what it is. It's really just this guy, but with a different name on it. So you can have pressure gradients, temperature gradients. I guess you could have magnetic gradients, and anything that has that kind of word gradient in it is talking essentially about this process here. So if you're wondering who uses gradients, they're the people that do it. If I was looking at a surface temperature thing and I found the gradient at a particular point, that would be saying if you're on this piece of mail and you go from this place to that place, right? If you go in that direction, it's going to get hotter the quicker. That's the fastest, that's the direction with the fastest increase in temperature. So are we good with how to calculate a gradient vector? It's really just 2 partial derivatives and then it's done. Okay, let's do something I haven't done. Keep the function very simple. Do you know there's no reason why you can't have a 3-dimensional gradient vector or a 23rd dimensional gradient vector? I haven't done this one, but I hope you have some insight into what you would expect the formula to be. So what do you think the gradient vector of this 3-dimensional function would look like?
Well, the first one would just be 2x.
Oh, you're telling me the answer, right?
Yeah.
And the
Second
second
would
would
be
be?
3y squared. And the last is 4z cubed.
Is there a kind of symmetry in the formula that makes it pretty obvious how you would find that particular gradient vector? So can you imagine there's a function with 10 variables? Wouldn't it just be x, y, z, whatever the next 7 variables were called, and that would be the gradient vector? Are we good? And just for completeness sake, if you have to find the gradient vector at a given point, 2 times 1, 3 times 2 squared, and 4 times z cubed, that would be your answer. So if that's cool, I want to move on now to returning to the directional derivative. Sorry, right? If there are any questions, this is your chance to ask. Okay, the directional derivative of a function, say z equals f of xy, in the direction u, a comma b, is given by this formula. In direction, big capital D, The little u with the little arrow above it is the vector u, and f or f of xy. Sometimes they put xy down, sometimes they just say f. And it's a dot product. It's a dot product of the gradient vector with the direction vector. So it's not that difficult to calculate, right? You know how to get the gradient vector, and you're told what this guy is. So you put that together, you're getting the direction derivative. So for instance, suppose you wanted to do x squared y plus xy cubed, and you wanted to find the directional derivative at this given point in that given direction. So we've got a function, we've got a point on that function, and we have a derivative, a direction to use to calculate the directional derivative. So this is probably not how you're going to do these questions. I'm pretty sure that once you get used to it, you're going to cut out quite a few of these lines. But I'm just going to take it slow, at least for the first one. So we are going to find the gradient vector first. And if you find this derivative, you get 2xy with respect to x, oops, almost missed it, plus y cubed. And if you do this guy, you get x squared plus 3x y squared. Okay, so there's the gradient vector. Now I'm interested in this question at a specific point. So I'm now going to find the value of the gradient vector at 1, 2. So that's going to be 2 times 1 times 2, add 2 cubed. Then 1 squared plus 3 times 1 times 2 squared. So the gradient vector at that one specific point is going to be 8 add 4, which is 12, and 12 add 1, which is 13. Now I already know the direction that I'm going to find the direction vector in. It's in this direction. So the direction vector of u, this function f, at the point 1, 2 is going to be the gradient vector dot product with the u, the direction vector. And so it's going to be 12, 13 dot 3, -1. And that's going to get me 12 times 3, add 13 times -1. So what's that? 36 take away 13. The answer would be 23. So if I went to some software and found out what this surface was like, and then I looked at 1, 2. So imagine the floor is 1, 2, then you'd go up to the surface directly above that point, and that point on the surface, if you traveled in the direction of this vector, you would find that the surface had a slope of 23. So if you imagine a little tangent line, that little tangent line would be sloping upwards at a very steep slope of 23. Suppose the direction vector, this number here, ended up being 0. What does that tell you about the surface at that point as you travel in this direction?
Wouldn't it be flat?
You're at a local extreme.
Well, not necessarily a local minimum, but flat is an interesting word because it could be, you know, it's maybe not a word I would use. Can you imagine it's like walking around somebody's belt? Your slope is 0, you're horizontal. So what I would say, a better way for me, a better way to say that would be, at that point, the surface is basically parallel to the floor, right? You're not going up, you're not going down. If it's positive, doesn't it mean that at that point, if you went in this direction, you would be going uphill quite steeply? And if it was -23, can you imagine in that direction, you'd be going downhill? So positive means at that particular point, traveling in that direction, you're going uphill. or negative, you're going downhill, or 0, you're basically just going sideways, right? You're not going up or down, you're parallel to the floor.
Is there a way to find at any point a direction where the slope was the smallest?
No. Oh, rewind that. It's not a question that they ask. And so while my brain is thinking of that, I will tell you that there is a way of finding which direction is the steepest. And the one that's the steepest is the value of the this fella here, right? The gradient vector at that given point. So see that direction there, 12, 13? That's the direction you would go if you wanted to go the steepest. Now you would say, well, what would that look like? Well, wouldn't that just be this guy, dot product, 12, 13, right? The same fella. Now, as far as is there a way to tell the slowest or lowest one? And I said kind of, no. I'm thinking about it now, and my brain is telling me that isn't, if you mean by slowest, do you mean, not slowest,
The smallest slope?
smallest slope. So that would be another way of saying the biggest negative. I'm thinking there might be a way to do that, but I'm not quite sure what it would look like. I'm trying to think in my brain, is it possibly that I haven't seen it anywhere? So maybe if you come across
like
it,
a maximum minimum problem.
it might be you take the gradient vector and try and find out where, for what value it's smallest, I guess. That would make sort of a sense, but the problem is that it's dot product with this guy. So now that I'm thinking about it, do you know if I find the general formula of this, right, just called this x's and y, well, just called this 12, 13, but I generalized this fella, called it AB, then I probably could figure out how to make it smaller by just solving the problem, what value of A and B make this the worst? It's an interesting question, Ashton, and I don't really have a good answer. I wonder if there is an answer. Hey, get famous, find out. If you discover it and no one else has beat you to it, it's going to be called the Ashton theorem, right? But a good question. I wish I had a good answer for it. I do know the maximum. It's the value of this fella, right, the gradient vector at that point. There's a theory that tells us that. But I don't know what the minimum is or the biggest negative is. And they call it the steepest, so that might explain it. Are we good so far? We okay with, good, okay. I'm just going to pick a random function and do it again. Suppose I have a function, this time it's going to be e to the xy plus sine of xy. So that's my surface. I'm interested in what's happening at the point 0 pi. And I'm going to go in the direction, at that point, I'm going to go in the direction 1, 1. Oh, let's make it -1, right? 1, -1. So just top of my head, create a question. Let's see where that travels to. The gradient vector is differentiate this with respect to x. Differentiate this with respect to x. You do get the cosine of xy. Do you get anything else?
Times y.
Okay. And now we'll go through a similar process, but now with the y's. That'll get you an e to the x just, and this guy will get you an x cosine of xy. And now I'm going to find the gradient at that given point, and we'll see what that looks like. So e to the 0 pi plus pi times essentially the cosine of 0, comma, e to the 0 plus, don't care, because 0 times that's just 0. So that's going to be pi, that's 1, so that's going to be pi. That's interesting. The gradient vector is 2 pi comma 1. Okay. Let's find out what the direction vector at that same point is. It'll be the dot product of those two. So 2 pi and 1 with a dot product of 1, negative 1. 2 pi times 1, add 1 times negative 1. It looks like in that particular direction, you're going to go uphill with a slope of roughly about 5. Like 2 pi minus 1 is about 5. Are we good? Do we need a joke? Because one just came into my head and I have to get it up.
Yes.
Okay, go for it. How do you stop a Polish tank?
I don't know. How do you?
You shoot the people pushing it.
Ha.
That's all I got. One ha. Okay.
I got one. I got one.
I clapped.
Oh, you did. I got some claps. I'll take it. Go for it, Kevin.
So how do you win an argument in Canada?
I don't know. How do you win an argument in Canada?
You don't. Both of you say sorry.
Oh, is it in, we're picking on Canadians. Okay, then. What is the difference between a canoe and a Canadian?
I don't know. What is the difference?
That, well, let's see.
Hmm?
Oh, I remember now. Canoes can tip.
Oh.
What?
Canoes can tip. I've been told that Canadians are not very good at tipping people in restaurants. Allegedly.
Oh, okay.
If I had an air horn, I would be playing it right now.
I'm not sure why. Why is that?
You know the little air horn
People
sound effect?
usually use it.
Oh, so that's a good sound.
Oh no, but I got this though.
Okay, I'm not sure we need that, but thank you anyway. Okay,
Why don't
so
eggs tell jokes?
it's kind of timing, yeah. So I have to do that. I know it distracts everyone, but in some ways it helps me as well because then I get back into focusing. So at this point in time, if I gave you a function, I told you a point, and I told you a direction, would you feel comfortable that you now know how to calculate what's called the direction vector? Would you feel that that process is pretty much a plug and chug situation, isn't it? As long as you know how to differentiate and evaluate things, you're never going to go particularly far astray. Now, there is a variation on directional derivatives, and it's still a directional derivative, but we tell you what direction to go, not by telling you go in the direction of the vector u 1, 2, but we just say go in the direction of theta equals pi upon 2 or theta equals pi upon 4. Do you see that if you look on the floor and you point in a direction, it's a bit, imagine the guy's on the hill and you just, instead of a compass, you've given them a big circle. You know, if you go 0, it's to the right. If you go pi upon 2, you go forward. What would be the steepness? That's essentially what the directional derivative is telling us. What would be the steepness of the hill if you traveled in an angle, in a direction of an angle called theta, right? So that's this guy. The directional derivative of a function in the direction of an angle theta is given by this formula. Hey, that's the same formula. You are right. And delta f is the same delta f. Have you noticed that u is now given as cosine theta comma sine theta? That wasn't just pulled out of the air. Can you see where these guys are coming from? Does anybody understand why that is cosine theta and why this is sine theta? Where it's coming from?
Sine has
Yeah,
respect to
sure,
y.
right.
And then
Yeah,
cosine
isn't
has
it the x and y coordinates? You know, r sine theta, r cosine theta, that kind of thing, right? That's all it is. So, okay, you have to memorize it, I guess you have to remember it. But once you've got that, it's still the same question, right? It's still find a directional derivative. They're just telling you the direction, for want of a better word, in terms of an angle rather than in terms of a vector, right? That's the only real difference. So let's take this guy and I'll do this first one slowly. So the gradient vector is going to be, well, differentiate this guy with respect to x, differentiate this guy with respect to y, partial derivative, of course. And with respect to x, this guy gets you sine y, plus with respect to x, you get 2xy. And then if you go back to this one and do it with respect to y now, you get x cosine y, and you get a plus x squared. Comfortable with that? It's usual gradient vector, nothing's really changed. The gradient vector at a particular point, in this case it's going to be 1, 3. Okay, I can live with that. It's going to be the sine of 1 plus 2 times 1 times 3, comma, 1 times the cosine of 3 plus 1 squared. Now, I know things like cosine of 3 and cosine of 1 or sine of 1 are not very nice things. We want exact values, and because we want exact values, we'll just live with it. And what I mean by that is that this thing is just the sine of 1 plus 6, and this guy is the cosine of 3 plus 1. The only time you would be doing more work here is, can you imagine it wasn't the sine of 1, but the sine of pi upon 6, or the sine of pi upon 4, in which case wouldn't you find the exact values of that because they are doable? But something like a sine of 1 or a cosine of 3, that's the best you could do. Its exact value is the sine of 1. Now, the direction derivative at the point 1, 3 is going to be our dot product. In this case, the sine of 1 plus 6, comma, cosine of 3 plus 1. And since we are doing it in the direction pi upon 4, won't this fella be the cosine of pi upon 4, and the other one's going to be the sine of pi upon 4. And if I'd thought ahead, I would have done this, but I'm now going to fix it. Wouldn't I turn that guy into root 2 upon 2, root 2 upon 2? If this had been 5,7 or something, right? Some weird stuff, wouldn't I just be calling it cosine of 5, sine of 7 or something, right? I would just call it whatever it was. Well, tidying it up, not really much of a tidy up, but root 2 upon 2 times all of this. Add root 2 upon 2 times all of that. And although there's not a lot I can do, I am going to do some stuff. Since I'm running out of room, I'm going to do it in one go. I'm going to distribute all this stuff, right? Or let's rephrase it. I'm going to take this out as a common factor and then just add these two things together. So what I would end up with would be a sine of 1 plus a cosine of 3 add 7. Are you happy about where that came from? I was about to say I would distribute it all, collect like terms, and then pull out the root 2 over 2, but it's probably quicker just doing it the way I said. So if you were on this surface, at that point, traveling in this direction, that's how steep the hill is. Okay, it's ugly, but that's the answer, right? Do we feel good about this? Cool. That seems to be going quite well. Okay, let's do my usual look at the homework. I thought I saw Lee here. Are you around here, Leah? I thought I saw
Yep,
you,
I'm
John.
here.
Yeah. How was your journey back?
It was pretty good. It's a long flight. We got a nonstop, so
Well, that's not so
fun.
bad. How long does that take?
About 6 hours.
Oh, God. Are you on the East Coast?
Oh, I was on the East Coast.
Yeah.
I'm back on the West Coast.
You're now
now.
back home, yeah. But that is, yeah. Yeah. When I go to Scotland, I know what long flights are, so I feel your pain. I think the people who make chairs on aircraft are masochists or sadists, whichever one it should be, because those chairs are good for about 1 hour. And then for the rest of that journey, my back kills me. So that's me.
Yeah, well, it was kind of nice because of COVID, they have the middle seats open. So it was just the baby and I in our row. So that was kind of nice.
Oh, that's cool. How young's the baby?
He's 2, or just over 2. So just old enough that he has to wear a mask the whole flight. So that was a bit challenging, but he did pretty well.
Okay. I think children have a problem with air flights, especially when their ears pop and they just don't know what the heck's going on. And they can get a bit grumpy. So, yeah. I've been in lots of aircraft with crying children, and for someone who's got no patience, I've actually got a lot of patience for them because the poor little things don't know what the heck's happening. So you can't really get grumpy about the kids crying. That's just what that's how they communicate. So I don't know, was your little fellow okay with that?
Yeah, he did pretty good. He got a little bit scared with the loud noises, and he's evidently terrified of airplane bathrooms. So that meant on the way back, he ended up sitting in a dirty diaper for a while, but the airplane bathroom is just too traumatizing for him.
He doesn't like it. Is it just it was confined?
Oh my gosh. Well, it's small, number one. It's really loud because it's at the back of the airplane. And when we were in there and he was freaking out and he was looking around, he accidentally flushed the toilet while we were in there. So that, of course, was
that was one more noise to scare the
and that was it.
out.
That was it. He was done. He was screaming bloody murder. It sounded like we were killing him back there. Flight attendant's like, is everything okay? Like, yeah, I'm just trying to change him. So we didn't even try on the way home. I just kind of let him sit and just cut back on the amount of juice he had.
Well, that's not going to be permanent. When they get older, they'll get over some of those fears. I find airplanes boring, but I'm not claustrophobic, so it doesn't bother me. Okay, well, everybody, I don't know. Can you see the homework section, or will I have to go out and in?
It's not there right now.
Okay, so it's an out and in then. Where the heck? Aye. Can you see it now?
No.
Okay, are we having... I'm zooming up and down. You can't see that. Okay, let's try it again. Was this the class that I got to say I got little funny circles and you all frozen me at the end? Was that another class I had? Huh.
I think that was another class.
It was another. Yeah. There we are. Third time lucky. Can we see it this time?
Yes.
Okay, so I'm just going to show you what these kinds of questions look like, just the way the WebAssign ask it, because sometimes they just make life weird. Right. Can you see in this case here, it's a pretty straightforward, here's the function, there's the point, and this is the angle. So that's very similar to the one I just did a few minutes ago. You agree? Now, you're going to have to find exact values for things like the cosine and the sine of pi upon 3 and pi upon 6. So you might want to get go looking somewhere and get those standard angles, you know, a little table somewhere handy, so that when you come to, oh, well, let's hit you with it. What's the cosine of pi upon 3? Right out of the blue. Cosine of pi upon 3.
1/2.
Okay. What's the sine of pi upon 4?
Square root of 2/2.
Okay. What's the cosine of negative pi upon 6?
Negative square root of 3/2.
Is it negative?
Positive, sorry.
Right, because it's in the fourth quadrant, and fourth quadrants are positive. So not only do you need to know the standard angles, you'll have to remember all sine, tan, cos. The quadrant also decides plus or minus. So that's just a memory thing, right? Let's just go back and look at trig tables and maybe write a little, you know, a little piece of paper at the side with all of them. Are we quite comfortable with the process of here's a function, here's a point, here's an angle? You feel those questions are pretty straightforward. There's no weird stuff going on, right? Now, looking at question 4, they're pretty much doing it the way that I did the examples. Can you see that the first thing you're going to do is write down what the gradient function is? Great. Now, here's the issue with WebAssign, not with you. If I was differentiating this thing with respect to x, would you agree the answer is 1/y?
Yep.
Right.
Yes.
Now, you got to get this into the calculator. Do you see this little fella here called vectors? See that little tab I just hit, vectors? See if I hit this one, do you see I now got the funny little shapes that I like using? So in this case, I would be going back to here, and I would go brackets. And the first fella was what, 1/y?
Yeah.
Right. So it's not that what we're doing is awkward, that sometimes you just have to figure out how to type the answer into the WebAssign so that it does it. If you just used the greater than and less than symbols that's on your keyboard that look exactly like that, it will come back and say you've got it wrong. Not because you got it wrong, but because you wrote it not using the correct keys, for want of a better way of phrasing it. Okay, what's the derivative of x over y with respect to y?
Negative x over y squared.
That's almost like a standard one, isn't it? Because I've seen that a couple of times now. So there's the negative going in, there's the fraction, and we'll put the x on the top, and then we'll go downstairs and we'll do the y squared thing. Excuse me, my keyboard's a little bit further away than I want it to be. There. Are we good? Right. Now, when you do this one, won't you basically just replace the x with 3 and the y with 1, and you'll write down things like 1, negative 1/9? I think that's what it would be. And then this guy, you would actually do some scratch work on the side. And I don't know what the answer is. It's 42, it's 17 thirds, it's negative 5/9, right? Whatever it is, then you put the answer in there. So don't turn things into decimals. It doesn't like them. It's
Now, I have a
probably
question.
okay. Yes, Leah.
Sorry, I noticed that they have U with the I and the J. Does that mean we have to put C and IJ, or we're fine to just use the brackets?
See this fella here? Is that what you're talking about, Leah? This?
Yeah.
That's how they write it. Do you know all I do in my brain is I call that 3/5, 4/5 with my little funny guys that look like that. So I just ignore the notation.
Okay,
Right.
so we can just
Now,
use the brackets.
You can use, I like using the brackets, but if you're more into the IJ, because I don't know, maybe engineers, IJ is the way to go. If you feel comfortable with doing everything in IJ, then when you hit the vector thing, which is over here, Do you notice that there's a vector, an I and a J? You see them there? You must use those. If you use the keyboard I and J, it's just going to say you're wrong again, right? So as long as you are aware that that's how you do it, you're fine, right? So this answer that I've just written, right, could equally have been written as equals, let's go down to vectors. Could have been written in this format. Excuse me. The reason I'm having so much trouble here is that I have to have my whiteboard on my table, and that means that my keyboard is dangling precariously at the edge. So if I'm not careful, it'll shoot right over the edge, and then I'll be not very happy because I'll have to spend 10 minutes crawling under the table to find it. So you're wondering what the hell's that. So do you notice that when you see it, how it's slightly bold? And in textbooks, isn't that the convention that I and J, any vector, is bold? That's why if you look really, really carefully, do you see that little u is a bold u? That's because that little u is a vector u. So you plug in the numbers, you say it's 22, you are good to go. Are you comfortable about how those questions where the direction is a direction vector instead of the direction is an angle, right? Because that's the two main versions of these questions. What's the direction vector going theta is pi upon 2? Or what's the direction vector where u is 1,5? That's the two main formats. So question 5 is really pretty much the same. So comfortable. Have you noticed by the time they get to question 6, they just say, tell me the answer? Although you probably should do A and B anyway, because you need A and B before you can get the answer. Get the answer. Is it, I will pause for a minute. Is there anybody in that group that you're looking at, 6 to 9, that look weird and you'd like to see how it's done? Because I can see one. Six, 7, 8, or 9. Which one of them is just different from what I've shown you?
I think 9's the only one that's three-dimensional.
Yeah. It's
Or I
not a
guess
biggie.
four-dimensional.
Yeah, technically it is. But it's a 3-dimensional vector on a 4-dimensional surface, so I guess that's weird. But yeah, I wouldn't do this one, but I'll do one like it. Let's suppose it's x squared plus y squared.
Can we
plus
send the
XYZ.
methods now for roll?
Perfect timing, thank you. Will you lot do that while I'm getting this thing set up? Say hi. I am so lucky I've got intelligent students who just keep me in my, keep me where I need to be. Okay. So imagine this is it's a 3-dimensional, it's a 4-dimensional function in a 3-dimensional world, I guess. And suppose that we want to find this fella at the point 1, 2, 1, and the direction that we're going to travel is 1, 1, negative 2, right? Just pick in some random examples of that. Would you agree that the gradient vector is really no biggie, isn't it? You can do it with 10 as well as 2. So you're going to get 2x, 2y, start again. This guy is 2x, and this guy gets you yz. That's better. Do it with y. This guy gets you 2y, and this guy gets you xz. And do it with z, you get an xy. That's better. So if you want to find the gradient vector at the point 1, 2, 1, it's 2 lots of 1 plus 1 times 2. My pen's going. Then it's going to be 2 lots of 2, because that's a 2. What else? 2 lots of 2 plus an x times a z, so it's a 1 times a 1. And then the last guy is an xy, so it's a 1 times 2. I'll just stick in a 2 there. So it looks like 2 odd 2 is 4. 4 add 1 is 5, and a 2. And so the direction vector at this point is really just going to be the dot product of those two guys. And the first one is 4, 5, 2. And the second one is 1, 1, negative 2. I'll do this in my head. 4 add 5 is 9. 9 take away 4 is 5.
I think I missed something. Where did you get -2 from?
Don't know. I can't read. So +2. 4 add 5 is 9 add 4. Looks like.
So it would be +2 at the top too, instead of negative.
Oh, this here is -2. That's why this is U. And this is 2. So your question was, pen's gone, where did this -2 come from?
Oh, where did the top -2 come from? Was that just there to begin with?
Yes, you were told that. In my question, you've been told that.
Okay, thank you.
Right. Here's the thing. That's a slope. That's a 3-dimensional surface. That's a 4th-dimensional surface with a 3-dimensional vector in it. Do you know you can't imagine that shape anymore? It's beyond human brain's comprehension. Secondly, do you notice that this kind of question, you couldn't really get theta equals pi upon 4. Because when you move up the dimensions, angles kind of aren't the same as they used to be, right? It's okay with the floor. You could say, 30 degrees pi upon 4, because that would be a direction to travel, but not. So, perfect timing.